Today we're starting chapter 24 in chemistry 3111. So this is the chapter on carbohydrates. And before we get into the main topics that are covered in the section or the chapter on carbohydrates, we have to revisit or at least take a quick peek at some of the topics that we looked at in organic chemistry 1 and also in this class. The first one deals with drawing chair conformations. And everybody who's hearing the sound of my voice knows what cyclohexane is. So if I draw a cyclohexane, it looks like this. You all know how to draw the chair form of cyclohexane, and you know how to draw both chair conformations. Anyhow, if I put an oxygen in the ring of a cyclohexane, I get this molecule here, and this is called tetrahydropyran. We use the acronym THP for short. And so when we're drawing carbohydrates, we're going to see that the ring of a carbohydrate is actually a tetrahydropyran ring. And just as a convention, we're always going to draw this conformation here when we're drawing the chair of a carbohydrate, and we're going to put the oxygen in the top right-hand corner. So we're going to be doing that a lot. If you want to go back to practicing your chairs, I don't know, that's even worse than the first one, okay? But you can get some practice in drawing them like this over and over and over. But that's the idea, is that you want to be able to draw a six-membered ring with the oxygen in the top right-hand corner. Well, you can see that what I'm dealing with here would be, kind of how you might draw a Haworth projection. But the convention that we're going to use for the Haworth projection in this class is this, where we're going to draw our six-membered ring, and we're going to, again, put the oxygen in the top right-hand corner. So top right-hand corner, top RHC, right-hand corner. All right, so we're going to see that, and then we're also going to see a lot of Fisher projections. And I'm sure you've all seen Fisher projections, especially in biology textbooks. You see Fisher projections that look like this. So we end up with something that looks like this. And we saw them way back in chapter 5 of Organic Chemistry 1 when we learned the Kahn-Ingold prelog rules, how to assign R and S at a stereocenter. And I don't demand that you memorize the structure of any carbohydrates. But I think the one that I have shown here in red, it's a pretty good idea to memorize this. This is called D-glucose. And if you look at your textbook, what it says is the structure of D-glucose should be at your fingertips. Well, that seems like a kind of a politically correct way of saying you should memorize it, okay? Acetals and hemiacetals, I don't have to draw those. You remember those from chapter 19. And then the reduction of aldehydes and ketones. We saw that in chapter 12, and then we looked at it in even more detail in chapter 19. So these are some of the ideas that you're all aware of already, and these are some things that are going to come up in chapter 24 when we're discussing carbohydrates. Sometimes you'll hear me just say sugars, and when we're talking about carbohydrates, sometimes people will say we're just talking about sugars, all right? So it says here, carbohydrates or sugars are polyhydroxyaldehydes or ketones. If you take a look at this molecule here, this is a different form of glucose, okay? What I drew on the previous slide was a Fisher projection of glucose, but this is also the structure of glucose. You can see it's got a total of 1, 2, 3, 4 chiral centers in the molecule, but you see that it has an aldehyde in it, and then we have, 1, 2, 3, 4, 5 hydroxyl groups, and so we say it's a polyhydroxyaldehyde. And we're going to see that some sugars like fructose, for example, which I'm sure you've read the back of a candy bar wrapper and you've seen fructose on there. Fructose would be a polyhydroxy ketone. And where do sugars come from? Well, I'm sure you all learned this way back in grade school, okay, when you would have learned about photosynthesis and how plants convert carbon dioxide and water into sugar. So they take carbon dioxide and water, and by the grace of sunlight that comes from the sun, okay, then we make sugars like glucose and cellulose and lactose and all cellobiose, all these sugars that are important for things to live, okay, for us to exist. And so if you think about it, where does all energy come from? All energy eventually, or if you trace it back far enough, it all starts at the sun, whether it's oil and gas or the food that we eat, right? All the energy comes from the sun. So the reason why there's so much energy in sugars is because there's more energy in the carbon-carbon bonds that are found in a molecule like glucose and the carbon-hydrogen bonds than there are in the carbon-oxygen double bonds of a molecule like CO2. Anyhow, I'm not going to ask you to write an essay or anything like that. about that, but you should be aware of what photosynthesis is. Well, now that we've talked about that, let's talk about the simplest kind of sugar that you can have. And the simplest sugar that we could have would be classified as a monosaccharide, okay? Sometimes we call those simple sugars. Glucose would be an example of a simple sugar. Fructose, again, I'm sure you've all read fructose before, or you've heard of things like high fructose corn syrup. Well, these are simple sugars, and they both contain multiple chiral centers. And so if you are wondering, why do we use Fisher projections so much, right? These are Fisher projections that are shown here on this slide. The reason why we use Fisher projections to represent these structures is because of the abundance of chiral centers. Look, we have 4 in glucose, and then we have 3 in fructose. And initially, when Emil Fischer was drawing the structure of glucose, at first he was drawing it like this, using wedges and dashes in a zigzag for the longest chain, okay? And there's nothing wrong with this structure that's shown here. However, he wanted a faster way to keep track of all the chiral centers, and that's how he came up with the Fisher projection. So the Fisher projection that you see here. Now, you guys should be aware of, when you look at a Fisher projection, we talked about these in chapter 5, that any bond that is horizontal is coming out towards you. So in other words, you can think about any bond that's horizontal as being a wedge like this. Okay, I'm not going to draw them all in. We don't have the time for that. Okay, and any bond that is vertical, you can think of it as a bond going back. Okay, it's a bond going back like that. Now, again, we don't have the time to put all of those in there, but that's what we're looking at when we're looking at a Fisher projection. Now, we classify monosaccharides using kind of two or three parts in a way here. So the first thing we do when we're classifying monosaccharides is we tell the reader, is it an aldose or a ketose? And you can probably guess where this is coming from. If you're looking at an aldose, it's something that contains an aldehyde group. So you see for this compound on the left, we have an aldehyde group here. Excuse me. So that would be classified as an aldose. Okay. If we look at this compound on the right, it's called a ketose. And you can see that we have a ketone. If I just circled these 3 carbons and the carbonyl in the middle, yeah, there's a ketone there. So now, if we have an aldose or a ketose, you've probably noticed that if you compare this aldose, okay, with glucose, which is also an aldose, you notice they have different number of carbons, right? Glucose has a formula which is C6H12O6, but if we go over to this aldose here, you can see it does not have 6 carbons. It has a total of 5 carbons. And so to classify them in terms of the number of carbons, we use a prefix, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, so on and so forth, and that indicates the number of carbons. So we can take a compound like this one on the left, and we can say it's an aldose, but we say it's an aldopentose because it has 5 carbons overall. We can take the compound on the right, and we can say, yes, it's a ketose, but it would be classified as a ketohexose because it contains 6 carbons. Give me a thumbs up if you're with me so far. Aldose indicates we have an aldehyde in our molecule. Ketose indicates we have a ketone in our molecule. We use the prefix di, tri, tetra, penta, hepta, hexa to indicate the number of carbons. And so glucose, if we go back to glucose here, how would we classify it? We would say that glucose is an aldose. Why? Because it's an aldose and it contains 6 carbons. If we look at fructose, we would call it a ketohexose. Ketohexose, because it has a ketone and it contains 1, 2, 3, 4, 5, 6 carbons in it. There we go. All right. Everybody with me on that? Everybody with me so far? Not going too fast? Aldose, ketose, tetrose, pentose, hexose, etc., etc. All right. Okay, so let's talk about the simplest aldose you could have. Okay, so in order to have an aldose, we have to have an aldehyde group like this, and then we have 1 chiral center in this compound, and then we have a methylene and a hydroxyl attached to it. And it turns out that this compound is called glyceraldehyde. Now you see that since there's a chiral center, we can have 2 forms of glyceraldehyde, right? These 2 compounds are enantiomers of each other. One of them we call plus glyceraldehyde because it rotates plane polarized light in a positive direction. The other one is negative glyceraldehyde. Why? Because it rotates plain polarized light in a counterclockwise fashion. Or we can call the one on the right D-glyceraldehyde and the one on the left L-glyceraldehyde. D being for dextrorotatory and L being for levorotatory. So again, glyceraldehyde or D-glyceraldehyde is not a compound that you are asked to memorize, but it's not a bad idea to have this structure as a feather in your cap, okay, to know the structure of D-glyceraldehyde. And I'm going to show you later on how if you know the structure of D-glucose, you kind of have the structure of D-glyceraldehyde already. So how do we know when we're dealing with a D sugar versus an L sugar? It's a really good question. It comes up a lot. And the way that you know you have a D sugar is you start at the top. We always put the most oxidized carbon, so most oxidized carbon at the very top of our Fisher projection. When you go all the way to the bottom, so we start here, 1, 2, 3, 4, 5, you notice that carbon 5 does not have a chiral center on it. Why? Because it's a methylene, okay? But you look at carbon 4, and carbon 4 is a chiral center. So we go to the last chiral center, last chiral center, and if the hydroxyl group on the last chiral center is pointing towards the right-hand side, then we say the compound is a D sugar. Okay, that's the rule. Doesn't have anything to do with whether the compound is causing light to rotate in a dextrorotatory direction. What it has to do with is that the compound is a derivative of D-glyceraldehyde, right? Because you see that D-glyceraldehyde's only hydroxyl is pointing towards the what? Pointing towards the right-hand side. Give me a thumbs up if you're with me on that idea. Is anybody with me? Can you guys hear me? Cha? Can anybody hear the sound of my voice? Just checking. Okay. All right. So there we go. So again, D sugars have the hydroxyl group at the chiral center farthest away from the carbonyl on the right-hand side. So hydroxyl group at the chiral center farthest from the carbonyl on the what? On the right-hand side. Oops, that didn't work. So hydroxyl group on the chiral center farthest from the carbonyl on the right-hand side in the Fisher projection. All right, so now when we talk about D sugars versus L sugars, okay, it says here dextrorotatory means rotates plane polarized light to the right. L means it rotates plane polarized light to the left, okay? That actually only necessarily applies to D and L glyceraldehyde, okay? That's the simplest possible aldose that we can have. When we talk about any other D or L sugar, all we're referring to is this, okay? If the hydroxyl group on the last chiral carbon is on the right-hand side, it is a D sugar, and if it is on the left-hand side, it would be what we call an L sugar. So you see that both of these compounds are D sugars, but you see that they rotate plane polarized light in the negative direction, okay? They both rotate plane polarized light in a counterclockwise fashion. So the conclusion is this: the D sugar, when we talk about D sugars, which are the naturally occurring sugars. So I'm going to put this here. D sugars are natural. L sugars, if you're wondering about those, L sugars are synthetic. So largely synthetic. They're not really produced in nature, so synthetic like that. Anyhow, a D sugar means the configuration of the furthest chiral center is R, meaning it's pointing towards the right-hand side, while the L sugar, which is unnatural, okay, has the S configuration at the furthest chiral center, or you could say the hydroxyl is pointing towards the left-hand side. Either way is fine. So all we're asked to do in this question 24.3 is determine whether each of the following compounds, so what does it say? Determine whether each of the following carbohydrates is a D sugar or an L sugar. Assign a configuration for each chiral center. After assigning configuration for all chiral centers, do you notice a trend that would enable you to assign the configuration of the chiral center in a carbohydrate more quickly? Okay, let's take a look at the first one. Okay, so the A. If we take a look at A, okay, we'll start with the first chiral center here. So if I just kind of zoom in here, we'll start with this chiral center. Now remember, the hydrogen is on a wedge, right? It's coming out towards us. And so if we prioritize, we're going to go from 1 to 2 to 3. like this. So we're going in this direction, which is counterclockwise, which would be R, but the hydrogen is coming out towards us. And so this stereocenter must be S. All right, everybody with me on that one? Now, if we go to the next one, okay, if we go to the next one, if we start with this one here, so we have 1, we have 4. Now here we have a carbon, oxygen, and hydrogen. Here we have a carbon, oxygen, hydrogen. So it's going to go 1, 2, 3 like this. So again, we're going in a clockwise fashion, which would be R. We reverse it because the hydrogen is coming out towards us. So the second one is also an S stereocenter. So we've got 2 S's. Now let's go to the next one. So this one here, this is going to be 1. This will be 4. So if we count, so here we've got a carbon attached to an oxygen, carbon, hydrogen. Here we've got oxygen, carbon, hydrogen. Then we've got oxygen, hydrogen, hydrogen. And here we've got oxygen, carbon, hydrogen. So we're going to be going from 1 to 2 to 3. So this time we're going clockwise, which would be, did I get that right? And then, which would be, no, but, oh, sorry, I was going in the wrong direction. We go from 1 to 2 to 3. There we go. That makes more sense. So we're going counterclockwise, which would be S, but the proton is coming out towards us. And so we end up with R. My iPad really doesn't want to cooperate. Anyhow, so we end up with R for this one. And then the last one, so let's scribble an R in here. So we'll do the last one here. And so we go from 1 to, so then we have 4 over here. This carbon is attached to oxygen, carbon, hydrogen. This carbon is attached to oxygen, hydrogen, hydrogen. So we go 1, 2, 3. So if we go like this, it's going to be S. So we reverse it, and it is R as well. So there we go. So we have S, S, R, R. And without spending too much more time on this, okay, what the conclusion that you draw is if the hydroxyl, if your hydroxyl is on the left-hand side, it has a configuration that is S. And if your hydroxyl has a configuration where it's on the right-hand side, its configuration is R. Okay, so this works for all of our OH groups. So we'll put here OH groups. Now, if you're wondering, why didn't you teach this to me way back in chapter 5 of Organic Chemistry 1? It just wasn't the right time, okay? It was a timing issue. Anyhow, but there you go. So now you can fill them in pretty quickly. You can say that this stereocenter, so if I take my red pen, this one is R, right? This one is R. What else? This one is R. All of these are R, but anyhow. So there you go. So that is how you assign the stereochemistry. Now, if you draw your Fisher projection with the most oxidized carbon at the top, you see that for all 3 of these. If the hydroxyl is on the right-hand side, the configuration is R. If it's on the left-hand side, the configuration is S. All right, so when it comes to aldotetroses, so we see that this compound here, deerythrose, is an aldotetrose, and it has 2 chiral centers. So if we want to determine the total number of stereoisomers, we have 2 to the power of n, where n is the number of stereocenters. 2 to the power of 2 is 4. But out of those 4, 2 are going to be 2 D sugars, and then we're going to have 2 L sugars. Well, I'm going to tell you right now that in Chemistry 3111, so I'll put here Chem 3111, we're going to focus on D sugars, okay? So we're not really going to worry about the L sugars in this class. But if we think about if we take a look at the 2 enantiomeric D sugars that we have here, deerythrose and D-threose, what we're doing is we're building off of D-glyceraldehyde. So if I draw the structure of D-glyceraldehyde, which was this, okay? So remember, if it's D-glyceraldehyde, the hydroxyl is pointing in this direction. So D-glyceraldehyde, all right? The hydroxyl is pointing on the right-hand side. So what we're doing essentially is we're adding an extra chiral center in there, okay? And then we have the possibility of the hydroxyl being on the right or the left. And so these are the 2, these are 2 enantiomers. Sorry, these are 2 diastereomers. Sorry, these 2 compounds are diastereomers, but they also have enantiomers. Diastereomers, which are L compounds. So L-erythrose and L-threose, but again, those are unnatural, and so we're not really going to worry about those sugars in this class. So If you wanted to, you could try to draw them. Okay, you just have to reverse the chiral center at both of them. All right, so when we get to pentoses, well, then we have 3 chiral centers, and 2 to the power of 3 gives me 8. 4 would be D sugars, and 4 would be L. Again, we're only really interested in the D sugars. And so we end up with these 4 aldopentoses, or D-aldopentoses, I should say. We've got ribose, we've got arabinose, xylose, and lysose. And yeah, anyhow, I won't go into the whole biochemistry of ribose or anything like that, but you might recognize one of these sugars in here. And again, D sugars are the naturally occurring sugars. Now, again, I told you, you don't have to have any of these sugars memorized because I'm going to give you the family of sugars for your quiz, okay? But as far as the aldohexose, it's not a hexose, it's called an aldohexose. As far as those go, we have 2 to the power of 4, which equals 16, but then we have 8 D sugars and 8 L. We're only interested in the 8 naturally occurring D sugars. We go from allose to altrose, and then we have D-glucose, okay, which is the one that I think I'm going to put a star by it because you should memorize the structure of D-glucose. Again, the textbook says you should have the structure at your fingertips, which is just a nice way of saying you should have it memorized. Anyhow, why is D-glucose so important? Because it's the most abundant monosaccharide in the universe that we know of. We'll put on Earth, okay? Most abundant monosaccharide on Earth. So that's why we talk about D-glucose so darn much. Then we have mannose, glucose, idose, galactose, and talose. All right, now this will be provided for you. So this is going to be on the handout for quiz. Okay, so you don't have to memorize the structure of D-glucose. I'm going to give it to you on the quiz, but it is handy to know it because it comes up so much in the class. But you see, we build off of D-glyceraldehyde, and then we keep going to aldotetroses, aldopentoses, to the aldohexoses. All right, so as far as the ketoses go, their family is a little bit different because you start out with dihydroxyacetone. It's the simplest possible ketose, and there's no chiral center. And so when you look at the ketohexoses, they only have 3 chiral centers. So there's half as many ketohexoses as there are aldohexoses. Okay, and again, you might recognize this compound here, D-fructose, right? So if you've studied a candy bar wrapper or talked about high fructose corn syrup or something like that. But there you have it. So let's take a look at a practice problem, see if we can do this. This question just says, draw and name the enantiomer of D-fructose. So if we go over to D-fructose, I put it in a circle here. So what I'm going to do is redraw it in a way that I can see it. So we have our ketone here, then we have 1, 2, 3 chiral centers like that. Okay, so let's pencil in chiral centers. This is me trying to be neat. So there we go. Put in our protons. Okay, so this is D-fructose. And so what we're going to do is we're just going to copy and paste this into the problem. So we'll copy it and we'll paste it into here. So to draw the enantiomer, all I have to do is paste the same structure, and all I have to do is reverse any chiral center. So we see that some of this didn't come out. So now all I'm going to do to make L-fructose, so let me get my eraser here, is I'm going to erase this, and we're going to call this L-fructose, and we just have to switch every chiral center. And so now our hydroxyl is over here. And now we have our hydroxyl on the left-hand side for these 2 chiral centers. And there you go. So we have D-fructose and L-fructose, and these 2 compounds are enantiomers of one another. There you go. So now you know how to draw a pair of enantiomers. You just draw the same skeleton in every chiral center. You just switch the side of the hydroxyl and the proton. And that is how you draw a pair of enantiomers, my friend. Not too bad. Okay. Give me a thumbs up if you're with me so far. We know what a D sugar is. We know what an aldose is. We know what a ketose is. We know what a monosaccharide is. We know that Fisher projections, the most oxidized carbon is drawn towards the top. We looked at the whole family of aldoses and the whole family of ketoses. I told you I'll give you both of these in the handout for your quiz, so you don't have to memorize the structure of any of these. We talked about how to designate a chiral center as being R or S. So if the hydroxyl is on the right-hand side, then it's going to be an R compound, and vice versa would give you an S compound. All right, so that's quite a bit of information, but let's move on. It says an aldehyde, if you remember from way back in chapter 19, an aldehyde and an alcohol with a catalytic amount of acid can react in such a way that we make a hemiacetal. And you guys probably remember that if you react with a second equivalent of an alcohol, that you can make an acetal. Well, that's not going to be fodder for this chapter. We're just interested in hemiacetals. And if you remember, I told you that hemiacetals weren't even all that stable. You see the equilibrium here is lying towards the reactants. And so that's not a great reaction. But it turns out that if your hydroxyl group from your alcohol and your carbonyl from your aldehyde or ketone are in the same compound, and if they cyclize, you end up with a what? Look, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And here 1, 2, 3, 4, 5, 6. If you end up with a 6-membered ring, well, we remember that 6-membered rings are very stable in organic chemistry. And so the equilibrium actually favors the products in this case. And so you end up with a cyclic hemiacetal. Now, why are we so interested in hemiacetals? It's because when we look at something like the cyclic form of glucose, for example, it turns out that the cyclic form of glucose actually is a hemiacetal. Let me show you. So this is something that you're going to be asked to do. If I give you a linear structure like this one here, this isn't D-glucose. It's neither here nor there. But anyhow, if we take our aldohexose, we see that we can rewrite the open form like this, where you're kind of twisting the chain, right? Because I told you that every vertical bond here is like it's going back into the page. So they just kind of knock it over on its side. But if we treat this with a catalytic amount of acid, we're going to protonate here, and then this hydroxyl can act as a nucleophile like this and create a hemiacetal. So check it out. We have carbon, oxygen, hydrogen. So this portion right here that I've just circled in black, that is a hemiacetal. Okay, but again, it's stable. You see the equilibrium lies on the side of the products. Why? Because we end up with a 6-membered ring, and 6-membered rings are favored in organic chemistry, right? So the 6-membered hemiacetal ring of the saccharide, we call that a pyranose or a pyranose. It depends on the person, potato, potato. We call that a pyranose ring, and that's based off of this molecule. I drew it earlier on. So if you have an oxygen inside a 6-membered ring, we call this tetrahydropyran, or THP, tetrahydropyran. If you have pyran, pyran is this compound, okay? Pyran is this, where you have 2 double bonds. So if you hydrogenate the double bonds, then you get tetrahydropyran, right? Because you've added 4 hydrogens to pyran. Anyhow, I digress. Now, it turns out that when you cyclize to make that hemiacetal, that you end up with a new chiral center. So check this out. This is actually a chiral center. Okay, where my little arrow is pointing towards carbon number 1. Check it out. Look, it's attached to a hydrogen. It's attached to a hydroxyl group. It's attached to an oxygen, and it's attached to this carbon down here. So yes, clearly this is a chiral carbon. So that means we could end up with 2 stereoisomers. So check this out. We could have either the hydroxyl pointing straight up or pointing down. So if it's pointing down, then we say it's trans to the CH2OH group on carbon 6. If it's pointing up, we say it's cis to that group on carbon 6. Or I think a better way of describing it is, since we always draw our Haworth projections with the oxygen in the upper right corner like this, I think it's better to just say if the hydroxyl is pointing down, okay, so we'll say here down. And who lives down in the water? Well, the answer is fish live down in the water. And so you see I made a little alpha symbol. Well, we call this the alpha anomer. Anomer is just a stereoisomer at what we call the anomeric carbon. So carbon number 1 is called the anomeric carbon. All right. So the alpha anomer the hydroxyl group on carbon 1 is pointing down, and right, and alpha kind of looks like a little fishy here, right? So maybe something like that. Anyhow, you get the idea. So alpha for down. And then if it's pointing up, then we say it's beta. Well, who lives up in the sky? And the answer is if you draw a beta and then you just kind of finish it like this, right? Butterflies live up in the sky, right? So that's kind of a mnemonic that my students gave me a number of years ago for remembering the alpha anomer, the hydroxyl group at the anomeric carbon is pointing up, and then the beta anomer is where the hydroxyl group at the anomeric carbon is pointing down. All right. So what we can end up with then is something called a mutarotation. So if you were to actually measure the quantity of each one of these stereoisomers, the alpha D-glucopyranose versus the beta D-glucopyranose. Remember, alpha is because this hydroxyl is down, and it's beta because this hydroxyl is up. Well, it turns out that if you were to put glucose in water, what you actually end up with is a mixture where it's 37% alpha and 63% beta. Now, here's what's kind of interesting, okay, is that the open chain form here, so this is open, this exists in less than 0.01%. So it's only present in a very, very tiny amount. But the idea is this, let's say you had pure alpha D-glucopyranose. If you had this compound pure and you put it in water, it's going to reach an equilibrium so that eventually you'll end up with 63% of the beta and 37% of the alpha. So there's nothing you can do about that, right? Anyhow, there you go. So that is what we call mutarotation, okay, where it's always going to interconvert. And there's no way to predict the amount of alpha that you're going to have and the amount of beta. There's no quick calculation we can do to determine that. All right. So with that in mind, now that we've discussed mutarotation, it says here the dynamic equilibrium in between the alpha anomer, that's where the hydroxyl on the anomeric carbon is pointing down, and the beta anomer. So we'll say here beta anomer, like that is in equilibrium between the two. Okay, and it's usually the alpha, or sorry, in the previous example, it was actually the beta that predominated there. I misspoke. Anyhow, so mutarotation is accelerated with acid or base. Either way, it's going to happen. And it says here that with some sugars, the alpha form predominates, but others, the beta predominates. And there's no easy way to tell that. There's no quick and dirty answer I can give you. Like this time, beta predominates. This time, alpha predominates. It's going to be a case-by-case situation. Now, when it comes to drawing a pyranose ring, okay, it says here a pyranose ring, which is this one here. This is a Haworth projection, and this is a chair here. Well, we can actually draw our pyranose ring as either a Haworth projection or a chair. Both of them are fine, but it says here in the slides that the chair is better. Why? Because it reveals the 3D conformation. It tells you which hydroxyl groups are axial and which hydroxyl groups are equatorial. So it turns out that this here is, this would be beta D-glucose, all right? And anyhow, it says D-glucose is the only sugar where all groups are equatorial. So if we go from the Haworth projection and we draw the chair conformation like this, what you'll see is this hydroxyl is equatorial, this one, this one, this one. They're all equatorial. So this is why glucose is the most abundant sugar on Earth. It's because all of the hydroxyl groups are equatorial and no ifs, ands, or buts. Now, when it comes to furanose, I'm not going to ask you a whole bunch of information that's shown in this slide here, because you can see that it forms a 5-membered ring or a 6-membered ring, depending on how it reacts. But this will come up. This might be of importance later on, but just know that furanose, you can form a 5-membered ring or a 6-membered ring, but it says here the 5-membered ring is a hemiacetal. And if you take a look here, this is furanose here, so this is fructose here. So we have carbon, oxygen, carbon here, and then we have carbon, oxygen, hydrogen here. So that's a hemiacetal, okay? And then we also have anyhow, so it's just going to be a hemiacetal. We'll just leave it at that. So we go carbon, oxygen, hydrogen, carbon, oxygen, carbon like that. So we'll put here hemiacetal. All right, there you go. Now, it says here the furanose form of D-fructose is the one that takes part in most biochemical pathways. But again, this isn't a class in biochemistry, so I'm not going to quiz you on that a whole lot. But what's kind of interesting about D-fructose is if you put it in water, you end up with an equilibrium between all of these, and you actually end up with 70% of the six-membered ring and about 23% of the furanose ring. All right, and you see that those don't add up to those that don't add up to 100. It adds up to what, 90, 93. And the reason why is because this is one anomer and this is one anomer. Well, we have two other anomers that aren't drawn on here. Anyhow, so with that in mind, it says draw a Haworth projection for each of the following compounds. So what I expect you to be able to do is to take that handout. So if we're asked to draw the Haworth projection of beta D-galactopyranose, we're going to go and we're going to find the structure of galactose, and the other one wants mannopyranose, so we're going to get both of those. So let's go all the way back here and let's get galactose. So galactose is this one shown here. So we've got the structure of galactose here, and the other one was what, mannose? So mannose is shown over here. So now that I've got those memorized, yeah, let's go back to the question, and I'll redraw them for you, okay? So if you, where are we? Right here. So let's start out by drawing galactose. We'll get the black pen here, and we'll say galactose looks something like this. So we have 4 chiral centers, then CH2OH. And let's get our galactose done. So galactose looks like this. We have 1 hydroxyl here, 1 hydroxyl here. There we go. All right, so that's galactose. And then for mannose, I'm actually just going to copy and paste this. I think it might save a tiny bit of time. Nope, not what I meant to do. So we're going to copy this and we'll paste it here. There we go. And then we'll just alter the structure. So for mannose, I'm going to have to move this and this. So, and then this one here and this one here. All right, so let's figure it out. So it's going to be something like this and then this. There we go. Oops. So that's D-galactose. So this is kind of running out of space here, but let me just move this over. So this would be D-galactose. And this one here would be D-mannose. Okay, so here's what we're going to do. So if you're not paying attention, wake up, because this is extremely important. I'll take a big drink of coffee here and I'll show you what we're going to do. Okay, so if you want to go from the open chain form, so these forms here, these are the open chain form, and then we want to go to the Haworth projection. So here's what we do. We're going to draw a 6-membered ring with the oxygen in the top right-hand corner. So just bear with me. I'll try to make it as neat as I can. So we're going to end up with something that looks like this. And then the next step is we're going to number the carbons. So 1, 2, 3, 4, 5, 6. Okay, so pay close attention. We've got 1, 2, 3, 4, 5. And the 6th one is going to be like this. We're going to draw a line straight up. And we're going to put CH2OH. Okay, and that last one, this is going to be carbon 6. And so what's essentially happening is the lone pair on the oxygen of carbon 5 is doing a nucleophilic attack on the carbon. Now here it's telling us that it's beta. So if it's beta, that means that at the anomeric carbon, the hydroxyl is going to be pointing up, right? So we're going to draw the hydroxyl at carbon number 1 pointing up. And again, it's because it is a beta compound. Now, as far as chiral centers 2, 3, and 4, these are what's left over are these 3 here. So here's how we're going to do it. Is anything that's pointing on the right-hand side will be pointing down. Anything on the left-hand side is going to be pointing up. So let me make sure I write this down. So if I take a look at these groups here, okay, if they're on the right-hand side, they're going to be pointing down, okay? And any group that's on the left-hand side is going to be pointing up. So I'll put down and up like this. So let's take a look. If I look at carbon 2, I've got a hydroxyl going straight down. I have a proton going straight up, but this is a bond line structure. I'm going to leave it out. If I go to carbon 3, the hydroxyl is going to be going up. So I draw a line straight up, and then if I go to carbon number 4, the hydroxyl is also going to be pointing up. So I'm going to put it up like this, and there you go, my friends. There we have beta D galactopyranose, just like that. So now what I want to do is take a short break, and I want you to try to draw this compound here. So we're going to use the exact same convention, where we're going to draw our pyranose like this, okay? You can even put the CH2OH group in here. This part never changes. In fact, I'll copy it and paste it just so you have it for reference. Just put it over here, okay? So this is where we're always going to start for a reference when we're drawing Haworth projections. So if it's an alpha compound, what that means is that the hydroxyl at the anomeric carbon is going to be pointing straight down like this. Now, for carbons 2, 3, and 4, we look at the Fisher projection. Anything that's on the right-hand side is going to be pointing down. Anything on the left-hand side is going to be pointing up. So now we'll have a hydroxyl group pointing up from carbon 2, a hydroxyl pointing up from carbon 3, and then if you look at carbon 4, the hydroxyl group should be pointing down like that. And there you have it, my friends. Okay, everybody with me on that? This is just a convention of going from an open chain form to a Haworth projection. Cha? Okay, so let's move on. In the next one, it says provide a complete name for the following compound. So what we'll do is we'll take a short break, and I want you to take this compound, and I want you to say, okay, well, now I'm going to reverse that concept. If I draw the skeleton of an aldohexose, 1, 2, 3, 4, now all I have to do is look at the hydroxyl groups, right? So if this is carbon 1, 2, 3, 4, 5, 6. If this is 1, 2, 3, 4, 5, 6. We look at the carbon at hydroxyl carbon number 1. Well, that's the anomeric carbon. And remember, this carbon is sp2 hybridized in the open form, so there's no chiral center there. If we look at carbon number 2, the hydroxyl is pointing down. And so it's going to be on the right-hand side, which means the proton's going to be on the left-hand side. If you look at carbons 3 and 4, the hydroxyl is pointing up. So they're both going to be on the left-hand side, like this. And then, of course, we're only dealing with D sugars in this class, D sugars. And so that means the hydroxyl group at carbon number 5 should be on the right-hand side like that. So we fill in all of our protons like that. And what do we end up with? We end up with, did anybody identify this compound from the list of aldohexoses? Could anybody identify this compound? You go back to that big list of aldohexoses. So this is D-galactose. All right, so this would be D-galactose. All right, a little bit of D-galactose in our lives. So let's see here. So what we'll do is we'll take a short break. I'd like to give you a chance to try to draw the chairs for these 3 compounds. So it's asking you to draw the chair. So remember, we're always going to use this form of the chair, like this, where the oxygen is in the upper right-hand corner for all 3 of these. And then for the last one, it gives you a chair, and it asks you to draw the open chain form. So remember, we're only dealing with D sugars in this class, so that's better, okay? So that means our last chiral carbon is always going to have the hydroxyl on the right-hand side, so we just need to fill out carbons 2, 3, and 4, okay, to get the structure of this compound. All right. And then after that, we're going to take a look at reactions of monosaccharides. All right, so we'll come back and we'll do questions 24.16 and 24.17. All right.